Assalamu alaikum. Welcome back. The pillar of the scientific method is the reliance on experimental methods to ascertain the validity of any scientific hypothesis. This means that if we want to check the validity of any scientific claim, the sole basis of judging that is what we actually observe after doing an experiment. So, because of that, it is essential that we learn about how do we perform experiments and how do we make measurements on these experiments. We are also crossing a milestone in this course, in this session, because we are starting the second part of this course. Up till now, we've been focusing on the first part of this course, which dealt with the science and art of network performance evaluation. From this session, we are starting the second part of this course, which deals with experimental methods of doing network performance evaluation. After the conclusion of this part, we're going to venture into simulation and modeling based network performance evaluation. We've earlier seen how important empirical observation is to the scientific method. And I will reproduce a quote I've already cited from one of the pioneers of the scientific method, Galileo, who said that the benefit of empirical observation is that we make judgments on the basis of visible certainty and we leave behind armchair speculation, because before the scientific method became commonplace, most of the knowledge was decided without actual recourse to practical experimentation. What the scientific method popularized was the notion that the validity of any claim has to be matched with actual observation. If the actual observation contradicts the theory, we would say that the theory is wrong and it needs to be improved. And also, whenever we're using any experimental method, we have to make measurements on that. And then we match the measurements from the experiment to what would be the logical consequence of the hypothesis that we're testing. If they both confirm each other, we would say that the theory is a good explanation of the model, of the system being modeled. If there is not a lot of confirmation, or the observation does not follow or does not match the logical consequence of the hypothesis, we think that the hypothesis has to be improved. So let's now talk about measurements, because measurements are essential to any experimental method. So in measurements, we seek to quantitatively express something that we can qualitatively define. So let's now cite a quote by Lord Kelvin, who said that when you measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. What this means is that if you can express something in quantitative terms, then we have an objective explanation of the quality that we want to model. But if you just have a qualitative explanation or a qualitative understanding of the thing being modeled, our knowledge is not as good as we would have if we were able to express it quantitatively. So today's session is about measurements and the usage of measurements in empirical methods. Let me outline the rest of this session. So firstly, I'm going to talk about what exactly is measurement, and I'm going to dispel some common myths about measurements. And then I'm going to talk of two theories of measurement which we will bank upon to explain what measurement really means. And then finally, I'm going to explain that all measurements don't necessarily have to be very complex and they don't necessarily have to require very expensive equipment. We would see that measurement actually is something which reduces the uncertainty of something that we want to measure, and this measurement is usually made in quantitative terms. So we just want to reduce the uncertainty. We don't necessarily have to eliminate all uncertainty. This is a common myth and we are going to address it in this session. I'm going to talk about some simple methods that we can use for measurements which do not require a lot of equipment, but just a general interest in experimentation and some thinking. So let's talk about measurements first. So one very common misconception dealing with measurement is that all measurements have to be exact, or they have to exactly and precisely define the thing being measured. And if we are not able to do that, we would think that this thing is immeasurable. But that is not the case, because in fact all measurements are already approximations. You will never have a measurement which is completely exact. So I'm going to break this misconception into two parts, initially talking about the fact that even all scientific facts are inexact, in the sense that they are not exactly true, because the scientific method itself is based on uncertainty. You would recall when we talked of the scientific method, I told you about the philosophy of falsification. And this is a very influential theory about the scientific method proposed by Karl Popper, who said that the defining feature of something being classified as scientific is that it is falsifiable. That is, you can think up of some experiment and some observation which will prove, or in a way falsify, your hypothesis. If your hypothesis is such that your claim is certain, 100% sure, and it cannot be falsified, we will not call it a scientific claim. And this will not be really in the realm of scientific investigations. So a very important claim in this regard was made by a British philosopher and mathematician, Bertrand Russell, who said that the entire edifice of the scientific method is actually based on the idea of approximation. And when a man tells you that he knows the exact truth about anything, you can be safe in inferring that you're talking to an inexact man, because all the scientific truths, all the models that we make of physical realities are essentially approximations. When we talked of models, we said that all models are wrong, not in the sense that they are useless, but in the sense they are just approximations of reality. So we have to keep this in mind, and also know that basically all science is inexact, in the sense that it can never be 100% sure. So because science is inexact in that sense, how can we expect our measurements to be exact? In fact, we would see that all measurements are approximations. So you can think of measuring something through some analog device. You may have used voltmeters in your laboratories, or you may have used a ruler with some defined resolution for measuring the length of something. Both of these values are actually continuous values. So the length of something, the voltage, these are all continuous values. So you can never exactly know some continuous value by a measuring instrument that has finite precision. And all practical devices have finite precision. They can never know the true value to infinite decimal places. So this is one fundamental reason all measurements are approximations. But we can talk and think of counting something as a measurement. Especially in network performance evaluation, we are interested in measuring the time between two events. So this time is a continuous variable, but if we are interested in the number of times a certain event happens, this would be classified as counting a discrete set of events. So this may be thought of as an exact number, but when we put this in the context of any scientific investigation, almost invariably this number is actually a statistic, not a parameter. Please recall our discussion on statistics and parameters. We said that statistics are actually numbers that we calculate from samples, and not from entire populations. And just because the fact that we do not have access to the entire population, we're going to have some random error every time we do another sample. So that is the case here as well. Whenever we calculate a new statistic or we count something again from a new sample, we would have a different value. And this would, dictate the amount of random variation we have. So if we think of numbers in the setting of any scientific investigation, we would come to the conclusion that almost all numbers are inexact. So we can then, dispel the myth that all measurements have to be exact. Already we know that all measurements are approximations. Some of them are better approximations because they measure at finer grained level of precision. Some of them are not as precise, but all the same, all measurements are approximation at some scale or the other. So a quote which someone who is very famous in the area of network performance evaluation, Neil Gunther, he says that all measurements are wrong. So don't get me wrong here. We've already talked of all models being wrong, all measurements being wrong. I'm telling you that today. The important point is something being inexact does not mean that you cannot use it. We actually find models very useful because they are more tractable than physical systems. Because we cannot exactly know some, the value we are measuring, the approximation that we can get is, the best thing that we can have, and it is very useful to us for most practical purposes. So this is very important. For most practical purposes, the measurements are good approximations. So this, I hope, clears up the misconception that a measurement has to be exactly correct to, in finite decimal places. That will never be the case. So now it becomes important for us to then quantify the amount of uncertainty that we have in our measurement, because all measurements have some uncertainty. So if we know this, then we can actually make better informed decisions, because we know there is some error. The next best thing that we can do is to quantify the amount of uncertainty that we have. So a famous physicist, Professor Walter Lewin of MIT, says that any measurement that we have in which the associated error is not given is essentially meaningless. And that is in fact very true, because if we do not know the associated error with the measurement, we cannot really make any meaningful conclusions from this. So let's now talk about how do we go about quantifying the uncertainty in measurements. So for this, we would refer to the figure on the slide now. You can see 4 subgraphs, and in which we would explain the idea of accuracy versus precision. So if you see the subgraph on the left hand side, you would see that all the values are actually close to the bullseye. If we take the analogy of throwing darts, we are seeing that most of the darts are near the bullseye. So this would be the case where most of your measurements are near the true value. So this is the case when you have high accuracy, and because most of the darts are close to each other, the amount of variation is less as well. So we would say that the precision is high as well. So now we can define what accuracy is and what precision is. Accuracy tells us how close our measurements are to the true value, and preciseness informs us about the spread of the measurements. Unfortunately, in many cases, we do not know the actual true value. If we knew the actual true value, we can calibrate our measurement. In cases where the accuracy is low but the precision is high, this would be the second subgraph. So you see that the accuracy is low because most of the darts are missing the bullseye, but they are very close together. So you have a precise measuring instrument, but it is miscalibrated. So if we know the true value, we can actually calibrate this instrument. But in most cases, most practical cases when we come to network performance evaluation, you will not have the luxury of calibration. So this then makes such measuring instruments problematic. We can also have the case where we have high accuracy and low precision. So this would be the third subgraph. So you have a lot of variation around the central point, but still if you average them out, you would be quite close to the true value. In the last subgraph, you would see that the readings are dispersed away from the true value, and also the average does not actually come out to be near the true value. So this would be the case where your device is having both low accuracy and low precision. It is important here to cite a quote which I've already cited in an earlier lecture from John Tukey, who said that it is very important and it is much better to be approximately right than to be exactly wrong. Because when we think that we are exact, it may be that we are exactly wrong. That is, we have a device which is giving us very precise values, but it may be miscalibrated, or it may be missing the true value by a large amount, and because of that we may have the wrong notion and the wrong idea that our device is very precise and we're hitting the true value. In such cases, we can make approximations, and if we are approximately right, in the case where your average comes out to be the true value, but you have a lot of variation around that, that is much better than being exactly wrong. So this would be a very important guiding principle when we set out to make measurements. So why do we have inaccurate measurements? So this may be because your device is having some bias, some systematic bias. Every time you use your device, it is going to give you, let's say, a lower or a higher value. Imagine a weighing machine. So if even before you stand on top of your weighing machine, if it already gives a reading of 3 kilograms, this tells us that the weighing machine has a systematic error. Every measurement that we make on this weighing machine would be giving us a value which is 3 kilo more than the actual value. So this is an example of a systematic bias. And also, a very important assumption that we make for statistical analysis is the assumption of independence of observations. When this assumption is not met, this actually leads to the case of systematic bias, which leads to inaccuracies. So let's now consider this. When we have correlation amongst different readings, so in that case, you can think that one measurement is contaminating other measurements because all of them are not independent. In such a case, your measurements may be biased. You may have a systematic bias which may affect the accuracy of your measurements. So to understand this, let's study some examples. So the first example that you can see on the slide now is the case where we ask, let's say, a set of students to measure a heavy stone. So they go about measuring this, they make one measurement and it comes out to be, let's say, 10 kilograms. And then they act a little naughty and they do not actually make a lot of independent observations. What they do is they go back and they make up 40 observations from this single observation. So they add a little to this observation and subtract a little from this observation, and then arrange all the readings that they make. Let's say they're making 40 readings in a haphazard manner. So someone who reads it may think that this is actual observation, actual measurements. But we can clearly observe that because the students have messed up the observations, any analysis based on these observations would be biased, because asal mein we only made one observation here, but all the other 39 observations are based on this single observation. In other words, all the observations are correlated. So because of this, you would have a natural bias in your observation, and whatever conclusion we draw from this experiment or these observation would be misleading. We can think of other examples in which we have the problem of statistically dependent sample items. So another example that we can consider is that we want to measure the average network congestion, and for that we make use of the ping command and we take the measurements of the round trip times. But if we do all these measurements at the same time, the chances are that the readings would be correlated, because if the network congestion comes, it would persist for some while. So if by chance you took your measurements when there was network congestion, you would actually maybe overestimating the amount of congestion in the network. If you took all of your readings at a time where there was no network congestion, you may be underestimating the amount of network congestion. So this highlights the importance of having independent sample items. So this is an assumption that we've been using all along. When we talked of samples, जब हमने random sampling की बात की थी, we assumed that all the items are picked at random from the actual parent population. But in practice, this is often not the case. And in all such cases, you would have inaccurate results. So the third example is actually related to samples. Imagine that you want to predict the result of an election, and on the election night, you go to an office of one of the candidates. Chances are that everyone who would be at that office would be supporting the candidate whose office they are in. So in such a case, you have a biased sample. Biased sample क्यों है? Because all the sample items are not independent. All the parent population is not represented. In such cases, we would have inaccuracies, which explain why in most measurements we have inaccuracies. Let's now talk about preciseness. So preciseness is a tricky issue because often even engineers rely too much on calculators without really understanding the basics of measurement. So a principle which we can use whenever we are making measurements, I would read this principle, and that is, when combining measured numbers, the final answer is only as precise as the least precise piece of data that went into the calculation. So to explain this, let's consider an example. Let's say we have a network and we want to check what is the throughput of this network. We make a measurement and we see that in 0.70 seconds, we're able to transfer 1.2 megabits of data. So now the question is, what is the actual throughput? So you must note here that the measurements that we've made are actually correct to two significant figures. So 1.2 megabits has two significant figures, and 0.70 again has two significant figures. So if we actually just input this calculation, because we know that the throughput is taken as the size of data transfer divided by time, and this gives us the throughput, the amount of data that we will transfer in unit time. If we simply copy these measurements into a calculator, you would get a value which is shown on the slide now. So while the original measurements were only correct to two significant figures, you see that the calculator is showing us meaningless preciseness. It is giving us a value of 1714285.714285714, but we cannot actually be so precise in our answer. The reason is that when we measured 1.2 megabits as the amount of data transferred, this may actually be a result of rounding off, or it may be that our measuring instrument may be rounding off, let's say 1.16 megabits to 1.2, just because it is giving us an answer to two significant figures. It may also be the case that it is rounding down 1.24 megabits to 1.2, just because we have two significant figures. So if the calculations that are going into measurement have less number of significant figures, you can never have a more precise answer at the end. This is something that many people forget, and because of this, many measurements are reported at a level which is more precise than it can actually be. So an example of this is, recently the United Nations Secretary General Kofi Annan, he went to Bosnia and he celebrated the birth of the 6 billionth baby in this world. So now the question is, how does he know that that baby is actually the 6 millionth human on this planet? Because this is just an estimate, and every estimate, every number has some error in it. So we can never be sure that, to this level of preciseness, that we can pinpoint that this is the 6 billionth baby. While it may be good as a political gimmick, but we must ensure that we do not repeat this mistake when we do scientific analysis. If we report something to a very high level of preciseness, whereas our measuring instruments and our calculations do not ensure that level of preciseness, this would be a kind of misleading with numbers. So we have to be very sure that we do not fall into this trap. So let me now outline some rules for measurements. Whenever we are making measurements, it is important that we replicate our measurement. We just do not base the thing that we are trying to measure by just a single measurement. Ideally, we should be taking multiple measurements, and then we can average out all these measurements. So the first rule is that the best estimate of a parameter that you want to measure is the mean. Take multiple measurements, take the mean, and that is the best estimate of the parameter that you're trying to measure. Now, as mentioned earlier, all measurements have errors. So our second rule then applies to quantifying the amount of error in our measurement. And this error in measurement is determined by the standard error of the mean. So you would recall when we talked of sampling, we mentioned sampling distributions, and we talked of the standard error. Standard error is a very simple concept. So if we are having multiple measurements, let's say we have 10 measurements, standard error is simply the standard deviation divided by the under root of the number of measurements. So if you keep on making more measurements, your standard error would reduce, or you would have a more precise value. This statement which I've just made actually has a mathematical basis, and that is the central limit theorem, which tells us that if we take a lot of measurements, the distribution of the mean is going to approximate a normal distribution, the width of which, or the standard deviation of which, is the standard deviation of the original population divided by the number of sample items. In this case, we can actually estimate the error of our measurement from just taking some measurements, and we take the standard deviation and divide it by the number of measurements that we've taken, the under root of that, and we would have an estimate of the error of our measurement. So when we have this error estimate, we should round this up to appropriate number of significant figures. And this actually depends on the number of measurements that you're making. In most practical cases, we should only report our error to one significant figure. For example, we can report our error as 0.001 plus minus. So this only has one significant figure, which is 1. All the leading zeros are non-significant. So in most cases, if we are reporting an error which has more significant figures than 1, this is typically because of over-preciseness. When you have a lot of measurements, let's say you are making 500 measurements, then you can quote your error to a higher degree of precision. When we talk of the fundamental constants in the physical world, the numbers which are standardized by the organizations which are maintaining standards, of Avogadro's number and similar numbers, these are the fundamental constants. इनकी भी precision सिर्फ 2 या 3 significant figures तक होती है. So you can imagine and extrapolate from there that your measurements typically would only be reported with a single significant figure, let's say 0.01, 0.1 and so on. A single significant figure would suffice in most practical cases. Let's talk now about the fourth rule. The fourth rule is that we must match the number of decimal places in the measurement that we're reporting. It must be matched with the standard error. So if your standard error is telling us that the standard error is, let's say, 0.1, then your mean measurement should also be reported to 1 decimal place. If your standard error is reported as 0.01, then your measurement should be reported to 2 decimal places. In all cases, we should synchronize both these things, the measurement and the standard error, because reporting the measurement to a higher degree of preciseness becomes meaningless. Lastly, the final rule is that all measurements should include information about the units. It is very fundamental and very basic, but many times we make this mistake that we do not report the units being used for our measurement. So this completes the first part of today's session, in which we talked of what exactly is measurement, and we dispelled some common myths about measurement. Let's now talk about 2 theories of measurement which will enlighten us about what measurement really is, so that we really understand it in a better light. Up till now we have shown that measurements do not have to be infinitely precise. Now we would define measurement as quantitatively expressed reduction in uncertainty based on 1 or more observations. And this definition is actually based on 2 theories about measurement. And the first theory is the theory of information. And this was proposed by Claude Shannon, and this is known as information theory, which is a mathematical theory which tells us the amount of information. So Claude Shannon came up with a theory, and he defined information as the amount of uncertainty being removed. So we can think of measurement as an information as well. So measurement is a better measurement if it reduces more uncertainty from the thing that we are measuring. So one important aspect that we must understand is that it is not necessary that we completely eliminate all uncertainty. A simple reduction in uncertainty will do. So to understand this, and to understand the concept of information and uncertainty in information theory, let's consider an example in which we have 3 coins. In the first coin, we have what is known as an unbiased coin, which means the probability of the coin being flipped and coming heads and tails, they both have equal probability of 0.5. In such a case, we have maximum uncertainty. And on performing the experiment, the observation that we make is the most informative that we can have with a coin, because a coin can only have 2 outputs. If both of them are equally likely, we have maximum uncertainty. And the measurement that we take in such a case would give us the most information. Now consider the case in which you have a biased coin. So if you consider coin number 2 shown on the slide, you would see that the probability of heads is 0.7 and the probability of tails is 0.3. So even before actually flipping the coin, we already have some information, or the amount of uncertainty in the flipping of this coin is less than the amount of uncertainty on flipping of the first coin, because in coin 1 both are equally likely, but in coin 2 one is more likely than the other. So in this case, the amount of information that we gain from this experiment is going to be less than the amount of information we gain from coin 1. So we can think of the information gained by a measurement as the amount of uncertainty reduced. Lastly, taking the extreme example, take the case of a biased coin in which you already know that it is going to come heads up. So probability of heads is 1 and the probability of tails is 0. In this case, no matter how much measurements you make, you're not going to gain any information because there is simply no uncertainty in this random experiment. You already know what will happen. So the cases that we studied earlier of correlation and statistical dependence, in those cases, you are removing less uncertainty by making repeated measurements. And the fundamental of statistics is that if you keep on making more and more measurements, you're going to converge to the true parameter value. That would not be the case when you have statistical dependence or you have other kinds of biases. So Shannon's theory actually captures the idea that we want, that measurement is not complete elimination of uncertainty, it is simply reduction in uncertainty. So to be some measurement to be classified and called a measurement, it has to remove some uncertainty. If it does not do that, we would not call this a measurement. The other theory that we would use to form the idea that we want to convey about measurements is the theory conveyed by Stanley Smith, and we've talked about this before when we talked of scales of measurement. So if you recall our session on summarizing data, we talked of the various scales of measurement. We talked of the nominal scale, the ordinal scale, and interval and ratio scales. We also said that data may be either qualitative or quantitative. An important idea is that while measurement is quantitatively expressed, reduction of uncertainty based on one or more observations, while we are expressing our measurement in quantitative terms, the measurement does not have to be about some quantitative variable. For example, we may be talking about some qualitative variable, and we may be talking about how much confident we are about something belonging to a certain set. Example, we've talked of nominal scales in which we classify the variable according to various categories and we assign them to various categories. So we can think of measuring some packet traces and seeing how much of the proportion is UDP traffic and how much of it is TCP traffic. We can also express these qualitative variables of TCP, UDP and other as numbers. So we are quantitatively expressing these qualitative variables. We can also talk of proportions. Our measurement can say that 77% of data is TCP, let's say the remaining is UDP. So in such a case, we are talking in quantitative terms, but we are talking about qualitative terms. So this is an important and subtle distinction. Also, apart from nominal scale, we mentioned ordinal scales in which you are assigning the variable to categories, but the categories also have some sense of order. So we talked of, let's say, the grades of a student. We can give the grades some quantitative numbers as well. For example, this is commonly done in colleges. A grade of A is given, let's say, a number of 4. A grade of B plus is given a quantitative number of 3.5 and so on. So we are expressing information about some qualitative variable, but we are doing that while using the language of quantitative numbers. Apart from these qualitative variables, we can also talk about quantitative variables, and we are familiar already about interval scales and ratio scales. In interval scales, the distances between labels are meaningful, but we do not have an absolute zero. So we cannot talk about length of some item. So for example, the date is an example of an interval scale. So we can talk about the difference between 1st January 2010 and 1st January 2011 is 365 days. But we cannot talk about what is the length of 1st January 2011, because this length of days is dependent on the origin. Where do we start counting? And the counting is actually starting from an arbitrary date, and we already know that there are different systems for assigning dates. So this is problematic, and we therefore conclude that for interval scales, the distances are meaningful but not the absolute lengths. In ratio scales, we can also talk in terms of lengths. So for example, we can say that this much amount of time has passed, because we can define time is equal to 0. So it has an absolute 0. We can also talk of temperature in Kelvin, because temperature, when it is measured in Kelvin, has an absolute 0. So when we have something that has that can be compared to an origin of 0, we would call this a ratio scale. And most of the measurements that we do in network performance evaluation would be of the ratio scale types. So with this distinction, I hope it is clear that measurement is just reduction of uncertainty, and we can talk about both qualitative variables and quantitative variables. So this really broadens our scope. We can now measure lots of things. So earlier, if with the definition that we have to exactly remove all the uncertainty, very few things would be measurable. But with this definition, many things become measurable. Let us now talk about how we can actually make measurements that are very simple and do not require a lot of equipment, and they just require some application of the mind. So we call such measurements back of the envelope measurements, because they are so simple that we can actually do them on the back of any envelope or any napkin. So this is a common terminology. We refer to such measurements as back of the envelope measurements. So the first example I'm going to give you is a rule of thumb. It is called the rule of 5, and this illustrates that we can know a lot about a population by just observing very few of the population. So from a very small sample size, we can make definite predictions about the entire population. So let me state this then, this rule of 5. The rule is, there is a 93.75% chance that the median of a population is between the smallest and largest values in any random sample of 5 from that population. So as an example, we may be interested in estimating median CPU utilization of a router in a day. So median CPU utilization of a router in a complete day, we can estimate it using a random sample of 5 independent measurements. The important aspect is, and I emphasize, independent measurements. So if your 5 measurements are independent, we can actually state with confidence, with 93.75% confidence, that the median CPU utilization would be between the highest and the lowest measurement that we get. So how does this come about? So the important point is that now we are talking of the median of the population. And if you recall, the median of the population is the midpoint. The probability of having a measurement which is above this median is 0.5. And the probability of having a measurement which is below this median is again 0.5. So when would we have a case in which you will not have the median in this range? That would be the case when all of your 5 measurements are either above the median or all of your 5 measurements are below the median. So let's calculate the probability of this. So the probability of one measurement being above the median is 0.5. the probability of all the 5 measurements being above the median is 0.5 raised to 5. So this comes out to be 1 over 32. Similarly, if we calculate the probability of all the 5 measurements being less than the median, that is again 1 over 32. If we add up these probabilities, we would have the probability of both these events, and these are mutually exclusive. Either they are above the median or they are below the median. So this probability is 1 over 16. So if we subtract 1 over 16 from 1, we get the probability that the range actually contains the median, and this is 15 over 16. This is from where we get the value of 93.75. So this is a very simple rule, something that we can always apply. We can take a random sample. This conclusion is based on the assumption that we are making a random sample. So if we take a random sample, we can apply this to many places, and this highlights the simplicity of this method. With this method, we can make many seemingly important measurements when the amount of uncertainty is very high. Admittedly, you would have many cases in which the range is very wide. अगर आपकी 5 measurements की range काफ़ी बड़ी है, it may not be very useful for you to know that the median is between a very large range. But in many cases, if the uncertainty is very high, even doing such a simple measurement can inform you a lot. So let's consider another example of an ingenious measurement method. And this was used by a very ancient Greek librarian who actually used this to measure the circumference of the earth. So the name of this Greek librarian is Eratosthenes, who was the chief librarian of the Great Library of Alexandria. So this is some 2200 years ago. So at that time, Alexandria was a center of high learning, and Eratosthenes was reading a papyrus book, and he read a very curious observation. He read that in a city which is south of Alexandria, a city known as Syene, in that city, during the longest day of the year, the book said that the sun is exactly above the ground in such a way that if you were to put a vertical stick on the ground, the sun will not cause a shadow to be created, which meant essentially that the sun is exactly overhead. So this was a little curious, but many people would just ignore this because this is a commonplace observation. How possibly could you predict Earth's circumference from this simple looking observation? What Eratosthenes did actually was he conducted an experiment. At the same day, at the same time, at noon on 21st of June, he performed an experiment and placed a vertical stick on the ground, and he saw that in Alexandria, we in fact do have a shadow. So to remove this discrepancy, he thought that the Earth must actually be a curved spherical body. And he then observed the measurement, he measured the angle being made. So if you observe the figures on the slide now, you would see that in Syene on noon on 21st June, the rays actually pass parallel to the vertical pole, and it did not cause any shadow. But the same day, same time in Alexandria, it was causing an angle of 7.2 degrees. So he extrapolated using rules of geometry that the angle between the two sticks, if we were to take it to the center of Earth, was actually 7.2%. So from that, he understood that 7.2% is 1/50th of 360 degrees, which is the entire angle if you were to make an entire circle. So to calculate the circumference, he needed the distance between Alexandria and Syene. And he got a person to pace out this distance, and it came out to be a measurement of 800 kilometers. So from that, he again inferred that if 7.2 degrees is 1/50th of 360 degrees, then 800 kilometers must be 1/50th of the entire Earth's circumference. So he calculated the Earth's circumference to be 40,000 kilometers, which is accurate to a few percentages. So this is not bad for a measurement which was done without any instruments and almost 2200 years ago. So this actually highlights the power of simple measurements, especially when we have a lot of uncertainty. The final method I want to talk about for making back of the envelope calculations is we talk about Fermi calculations. So this the name of this method is actually attributed to Enrico Fermi, a famous Italian American physicist who also got a Nobel Prize, who was famous for making casual looking estimates of important things that we wanted to measure. So he is famous for actually measuring the TNT yield of the first ever atomic bomb test, and he actually did it without any instruments. So he was at his office, and at the same time at the test site people were actually going to make the first atomic test, and before that there was no precedent for this. So what Fermi wanted to do was to estimate the amount of TNT being used, or the amount of TNT yield. And for calculating that, he actually shred the paper of his notebook and made it into paper confetti, and when the pressure wave from the bomb explosion came, he just blew them into the air and estimated from some fundamental physical principles that the TNT yield should be approximately 10 kilotons. And the actual estimate, which was made after a lot of deliberations and using a lot of equipments, it came to be 18.7. So this simple estimate is the basis of what we now know as Fermi calculations, which is very important. When you have a lot of uncertainty, even estimating to the near order of magnitude, this actually is a big improvement from your current state. So a famous question which Fermi put to his class students was how many pianos are there in Chicago? He was teaching in the University of Chicago, and the reason he gave this question was that this question is seemingly immeasurable, because how would anyone know this? But he showed that with thinking with method, you can break down this problem into subparts and make estimates for each subpart correct to an order of magnitude, and you would get an answer which is remarkably correct. So to illustrate this, let me give you an example which is closer to our homeland, an example about cricket. So if I ask you offhand, without you recoursing to any online method of determining statistics, that how many balls have been bowled in test cricket up till now? So I bet you would be stumped if you hear this question, because even the most enthusiastic cricket follower would probably not know this, and many people would actually just give up listening to this question. This is an example of what a Fermi problem looks like, but this is actually solvable to an order of magnitude if we think of this in parts. So let's do that. Up till now, approximately 2000 cricket test matches have been played. So each test match has approximately 3 to 4 innings. It is supposed to have 4 innings, but many times you have, due to rain, lesser innings. So imagine that we make a lower estimate of 3 innings per test match and a higher upper estimate of 4. So to make an estimate from these two estimates, we take the geometric mean, because the geometric mean is the same factor away from both the estimates. So this would be the under root of 12. Now we know the number of innings per match. We can calculate the number of overs per innings. Again, some innings close in lesser number of overs. When it's a good batting pitch, you would have a lot more overs being played. So we would have an estimate, lower estimate of 60 and an upper estimate of 100, and we again take the geometric mean of this. So the geometric mean of this is the under root of 6,000. And then we can calculate the number of balls per over. And again, many of you would not be knowing, but historically, we had different number of balls per over, sometimes 4, 6, 8. Also, you have the problem of wides and no balls, which classify as balls, but the length of the over is increased. So we estimate lower estimate as 6, the upper estimate as 8, and the geometric mean of this would be under root 48. So now we are in a position to estimate the number of balls being bowled, and if we do the calculations, this comes out to be 3.7 million approximately. So we made a lot of guesses, but we now have a figure, and we can approximately say that this is the number of balls being bowled in Test cricket. So to ascertain the validity of this and how close we were, I actually visited one of the cricket statistics sites, and I got this figure. The actual figure is 4.1 million approximately. So this is not bad for an estimate. In fact, this is too good for an estimate that we made. Most of the times you would not have such a good estimate. Many times you would be a factor of 2, 4, or even a factor of 10 away. In many cases, when you have a lot of uncertainty, such a method is useful. So let me now finish and wrap up this lecture. We've talked of measurements being very vital for experimentation. We've said that all measurements are approximate, and therefore we need to quantify the amount of uncertainty in a measurement. And lastly, we've talked of some basic measurement methods which may be useful when you have a lot of uncertainty. So I'll see you next time, inshallah. Assalamu alaikum.